In this video, we want to look at the topic transformers in physics. So we'll be looking at what transformers are, then we'll look at the parts of a transformer, how to draw a transformer. Then we'll proceed to look at the various types of transformers that we have. So we'll look at the step-up transformer, the step-down transformer. Then we'll look at the relationship between some particular parameters that we'll be mentioning when we are drawing the transformers, the relationship between them, how the transformers step up or step down, and EMF. We'll be looking at that, and then we'll be solving some practical questions on this. After that, we'll conclude the tutorial by solving some WIEC past questions on this particular topic, transformer. So this is bound to be a very detailed lectures or teaching on transformers. So get your notebook, get your pen ready, get your calculators ready, because we are about to dive in. All right, so the first thing we'll do is look at the theory part, look at what transformers are, and then the relationship between the transformers. After that, we can look at the calculation part in the next chapter. So what is a transformer? A transformer is a device used to step up or down an alternating current. So let's write that. We are saying a transformer is a device used to step up or down an alternating EMF. Okay, an alternating electromotive force, or basically an alternating voltage, right? So this is what a transformer is. It is used to either step up or step down an alternating EMF, right? That's basically what a transformer is. So let's have a general overview of what a transformer looks like. So basically, a transformer has what we call a soft iron core. So I'll draw the iron core like this. Okay, it has something like this. Then it has, let me use a different color here. So it has some things here, some coils around it. Okay, so this coil has a name. We'll be looking at that. Then over here too, we have another set of coil over here. Okay, and then we have over here our the source of our alternating current. Okay, connected over here, and then yeah, we have label this part. So basically, it's just the iron core, the coils, these two coils, and then a source of alternating current attached over here. So let me quickly label the parts. So this guy is what we are calling the soft iron core. Okay, that's the soft iron core. Then this is the AC input, alternating current input. This is our source of alternating EMF. Okay, now the first coil near the AC input is what we call the primary coil. So this guy is what the blue one, the blue coils over there, is what we are calling the primary coil. Okay, now it has, you can see that the coil is wrapped around the soft iron core for a number of times, right? That is what we call the number of coils, okay, or the number of turns. So we use N subscript P to represent that. Okay, so the number of primary coils. Okay, so NP, so we say this is NP turns. Okay, over here we have this. Since this is the primary coil, this is obviously the secondary coil. And then the number of turns is what? NS. Okay, Okay, number of secondary coils, okay, turns. Okay, that is that. So we have the soft ion core, the AC input, this over here, and then this is where we have the okay AC output. AC output. Are we okay? But then the distance between the this over here to over here is what we are calling the secondary EMF, okay, or the secondary um, potential difference. And then the distance from over here to here, okay, over here is what we are calling EP, which is the primary EMF, right? The source of primary EMF in the core, right? You can see that it is in line with this over here, okay, this side over here, okay. Basically, this white one is just for labeling purposes. Okay, so this is basically a general overview of what an alternating current a transformer is, right? So it has a primary core, a secondary core wrapped around a soft ion core, then it has an AC input and then the AC output. Now where the primary coil is, the EMF over there is what we call the EMF of the primary coil, which is represented by EP. Then the output, where the output is, we say that is a EMF of the secondary coil, so we represent that by ES. Obviously the coil on the secondary side is what we call the secondary coil. The number of turns it has is represented by NS turns, and then the primary coil, where the AC input is the primary coil, and then the number of turns is the NP. Then so basically let's have a look at some things we can note over here. So we are saying that it consists of a soft iron core with two coils wound on it, right? So it consists of a soft iron core, with two coils wound on it. Okay, another thing we should know is that the first coil is what we call the primary coil. So the first coil is the primary coil. Then obviously the second coil is the secondary coil. Very good. Now the primary coil is connected to an EMF source. Okay, the primary coil is connected to an EMF source. Okay, so which is the AC input that we have over here. So this is basically the description of what a transformer is. Now let's make some deductions from this, right? So let me make here deductions. Okay, let's do some deductions and see how best we can move from there. So the AC flowing through the primary coil is changing at all times, hence it produces influx in the secondary coil. So the alternating current, okay, flowing through the primary coil over here produces what we call influx in the secondary coil. That is what we need to know. That is the one of the deductions. We'll be using these deductions to derive the formula. That is why I'm taking my time to go through. So we are saying that the AC source or the AC flowing through the, I'll use this as primary. So through the primary coil is changing at all times. hence produces change in flux in the secondary coil. Okay, so it produces change in flux in the secondary coil we have over here. Now another thing is that flux that is produced in the secondary coil, right? The flux produced in the primary coil is proportional to the number of turns and then the current moving through the coil. So if we look at the primary coil over here, the flux produced by the AC input, which is inducing another flux to be produced in the secondary coil. The flux produced in the primary coil is proportional to the number of turns that we have over here, right? The NP. The number of turns on the primary coil, okay, determines the influx of the number of flux or the amount of flux that will be produced, right? So the flux produced by the primary coil is proportional to the number of turns NP and the current IP, okay? And then automatically, if we come to the secondary coil as well, the induced EMF in the secondary coil is also proportional to the number of turns NS and the current IS, which is flowing through it. So we are saying, basically, let's quickly make that. So we are saying the flux produced in the primary coil, okay, is proportional to the number of turns to the number of turns. Okay, the number of turns for primary is NP, okay, and the current IP, okay, which means the current in the primary coil. Now the other way around is true for the secondary coil, so I will not write that, you just quickly say it. So you can write this down. For the next deduction, it's the induced EMF in the secondary coil is proportional to the number of turns NS and the current IS flowing through the secondary coil. Okay, so we are saying that depending on the number of coils that we have on the core, okay, on the soft iron core at the primary side, it determines the number of current that or the amount of current that will flow through that primary coil. The same with the number of turns on the secondary side of the transformer also determines the amount of current that will flow through. Okay, there's a relationship between that. So let's look at that relationship now. We don't know whether they are directly proportional or indirectly proportional, but let's look at, so then the relationship is the current flowing through the primary coil, okay, over the current flowing through the secondary coil is equal to the number of turns in the secondary coil over the number of turns in the primary coil. Okay, now if you look at this is inversely proportional, which means that for the number of current flowing through the primary coil, it is inversely proportional to the number of turns of the coil, right? And then the same thing, the number of the amount of current flowing through the secondary coil is also inversely proportional to the number of turns on the secondary coil. Okay, so this is the relationship. So if you divide this by this, you are going to get this expression. So this is a very, very important expression that we'll be using in our calculation. So we need to hold this expression very, very deep. All right, so let's look at another expression which we'll also be using. So another expression we'll be using, okay, so before we look at that expression, let's look at something. Okay, now if no energy loss occurs in the transformer, then the power output is equal to power input, right? So let's take again. Okay, so we are assuming in an ideal situation where the transformer is so good, so perfect that no energy is lost during the step up or the step down process. Okay, then power output is equal to what? Power input. So let's look at that. So if no energy loss, if no energy loss occurs in the transformer, if no energy loss occurs in the transformer, okay, then the power output, is equal to what? Power input. Okay, so basically, what is power? Power is, okay, power is equal to voltage multiplied by what? Current. This is power, right? Now if this is power, in this case we are saying voltage can also be EMF. Okay, so power in our case over here will either be what, let's say if you are saying the primary power, okay, the power in the primary coil, it will be what? EP IP. Okay, then the power in the, so okay, so let me say primary power, so the secondary power, okay, which is the output, the power output. So the primary power is the power input, so this is the power input, and then this is the power output. Okay, so that will also be equal to what? ES IS. Are you okay? So we are saying that if no energy loss occur, then ES, okay, IS, which is the power output, should be equal to EP IP. Okay, power input, or you can rewrite them as this. Okay, is equal to IP on IS. Are you okay? So we are saying that it's either this or this, right? So this is just like you dividing, making the E stand at one place, and then the current also at one place, the EMFs at one place, and then the current also at one place. So this is the expression that you get. Now remember, earlier on we also said that IP over IS is equal to NS over what? NP. Okay, that is what we looked at over here. So this expression, okay, is what I am quoting over here. Okay, now so if ES, okay, the EMF in the secondary coil over the EMF in the primary coil is equal to the current in the primary coil over the current in the secondary coil, and then again this current in the primary coil over the current in the secondary coil is equal to the number of turns in the secondary coil over the number of turns in the primary coil, then we can see confidently from here that our ES over EP, okay, which is equal to IP over IS, is also equal to NS over NP. Okay, now this is a very useful expression that you are going to be needing for all your calculation. It's two things, right? You either take this expression, okay, and know them off head, or you just know this one off head, and then you are good to go to solve any problem on transformers. Now note that for the EMF and then the current, the relationship is inversely proportional. Are you okay? And then for the current and then the N, the number of turns, it is also inversely proportional. Are you okay? But if you want to take just the EMF and then the number of turns, they are directly proportional. So you can see ES at the top here, NS at the top here, EP at the top here, NP at the top here. So if I want to write this in another way, I can write ES over EP is equal to NS over what? NP. Okay, because they have this in common, so it means this is also equal to this. Okay, so basically this is equation 1, this is equation 2. From equation 1 and equation 2 we can get this as equation 3. Okay, don't confuse the positions. Are you okay? So the first thing you need to know is that the current and then the number of turns are inversely proportional, and then this guy is also like this. And once you know that, you don't have any problem, right? So like I said, the ES is the EMF in the secondary core. So this is ES is the EMF in secondary core. EP obviously is the EMF in the primary core. IP is the current in the primary core. IS obviously is the current in the secondary core. NP, okay, is the number of turns in primary core, and then NS is the number of turns in the secondary core. Very good, right? So this is the expression that we'll be using. So the ratio above, this ratio, okay, this ratio proves that it is possible to produce a higher voltage from a lower one, and then the vice versa, right? So from this expression, okay, you can produce a higher voltage from a lower one. You can also produce a lower voltage from a higher one, right? And that is what brings the two different kinds of transformers that we have. So if the output voltage, right, the output voltage, okay, if the output voltage is greater than the input voltage, then we say the transformer is a step up transformer. This is a step up. Okay, it's like you have a device, okay, you give it one apple and then it produces, let's say, three apples. Are you okay? It has increased the number of apples that you have. So if the output, which in this case the voltage output, is more than the input, then we say it is a step up transformer. Okay, this is one. On the other hand, if the input voltage, so if the input voltage is greater than the output voltage, then we say that this type of transformer is what we call a step down transformer. Okay, and that one again, I'll use this scenario again. If I have a device, okay, or a transformer that I give, let's say, three apples, and it gives me, let's say, one apple in return, right? It means it has lost some amount of two apples, right? It has reduced the number of apples that I have. So that is a step down. Are you okay? Very easy. So let's now that we know these expressions, and we know the formulas that we'll be using in our calculations. So the formulas that we'll be needing is this formula 1, this formula 2, and then this expression 3. Okay, or you can just know this in your head. Okay, this is a combination of all these three formulas. Once you know all this, you don't have any problem, right? So now we've looked at what a transformer is. We looked at the components, okay, what makes up a transformer. We also looked at some deductions. From the deductions, we're able to establish some of these formulas that we'll be using in our calculation. We also say that if the output voltage is greater than the input voltage, that is a step up transformer. And then if the input voltage is greater than the output voltage, we call that a step down transformer. Now let me quickly draw what a step up and step down transformer looks like, and then we can continue from there. Mind you, this is the expressions that we are going to be using for our calculations. All right, so let's look at the two types of transformers that I said. Let's look at their drawing, right, to know what is the difference between a step up transformer and then a step down transformer. See, the only difference between a step up transformer and then a step down transformer is the number of coils okay, the number of turns on the primary coil and then the secondary coil, right? It's just the number of turns. So for instance, for a step up transformer, we still have our iron core like this. Okay, we have our soft iron core. Then for a step up, then it means that the number of coils on the primary, okay, side will be less. Are you okay? So because the number of coils over here is less, the input voltage will also be less, right? But then because it is a step up transformer, then the number of coils on the secondary part, okay, so the secondary core will be more than the primary core. Okay, now because that is more than that, the output voltage will be higher, and that is how come it is a step up transformer. Okay, it's just the number of cores, right? So everything else is still going to be the same. So we have our alternating current source or our AC source over here. This is our AC input. Okay, and then the distance from here to here is our primary EMF. Okay, and then the distance also from here to here is our secondary EMF, and then we say this coil is our secondary coil, okay, which has the NS turns, okay, and this part is our primary coil, okay, which has NP turns. Are you okay? And this is our AC output, okay, where our output is going to be at. So this is what we are calling a step up transformer. It's a step up because the number of turns over here is small, so the input EMF, okay, will also be smaller. But because the number of turns on the secondary coil is much higher, the output voltage will be higher. And since output voltage is more than the output in voltage, it is a step up transformer. Now on the other hand, the opposite is true. If we have our, so this is the soft iron core, right? So if we have our iron core, okay, that looks like this. Don't mind my drawing. And then on the primary core, okay, the primary core, the number of turns is plenty, right? So we have a lot of turns over here, but then on the secondary side we have, let's say, just a few number of turns, okay, something like this, okay, 4 out of 1 2 3 4 5 6, let me even add more here. Okay, so if you look at this, obviously the number of turns on the primary side is more than on the secondary side, right? So therefore, so let me complete the drawing. So this is our AC input, okay, and then the distance from here to here is our input EMF, or our primary EMF, and then over here is our secondary EMF. Are you okay? And this is also our AC output. Okay, these are obviously our secondary core. These are obviously our primary core. Now our primary core has what? NP turns. Okay, and then our secondary core has NS turns. Okay, this is our soft iron core, right? So if you look at this, this is what we call a step down transformer, because the input EMF is very high, but then the output EMF or on the secondary EMF will be very small. So since the input EMF is higher than the output EMF, we say this is a step down transformers. Are you okay? So these are the two types of transformers that we have. Now that we know what a transformer is, we've seen the details, we've seen the formula that we will be using. We said that the uh, secondary EMF over the primary EMF is equal to uh, the primary current over the secondary current, which is equal to the number of turns in the secondary coil over the number of turns in the primary coil. This expression, we can use this side as 1, this side as 1, and then just this and this also as 1, right? So we can get all our formulas from here. So now that we know this expression, let's go ahead and have some fun solving some problems on transformers. Okay, so finally we are at where we will start solving some problems on transformers. So we have this particular question, so let's give it a try and see what our results will be. So the question reads: a transformer with 5,500 turns in its primary coil is used between a 240 voltage AC supply and a 120 voltage kettle. We have to calculate the number of turns in the secondary coil. Okay, now this is fairly easy, straightforward, no much turns are on it. So let's look at our solution, right? So they say that transformer with 5,500 turns in its primary coil, so it means the number of turns NP in the primary coil is 5,500 turns. Okay, it say it's used between a 240 voltage AC supply, so the supply, which is the input voltage, right? So it means EP, okay, the primary voltage is 240 volts, and then a 120 voltage kettle, right? It means the kettle, if you plug it, is going to draw out 120 volts, so which is the secondary voltage or the secondary EMF, right? So our ES is 120 volts. So we have to calculate the number of turns in the secondary coil. That is what we do not know, right? So if you look at this is very easy, very simple. We said that the ratio of EP, okay, EP over ES, okay, is equal to, sorry, here is okay, is equal to NP over NS. Are you okay? This is the expression that we said is true. So if you look at this, no matter which one you bring first, make sure you change it proportionally. So if it is ES, we are using this and this, right? ES, NS, EP, NP, right? So over here, I interchanged it, okay? Either this, or you can bring the ES first, then the EP is equal to, make sure if it is ES at the top, it is NS at the top, and then NP at the bottom. Either way is going to give you the correct answer, right? So let's do our substitution. So let me use this one for the sake of consistency, right? So our secondary EMF is what we said, we have 120 over our primary EMF is what we have over here as 240, and this is equal to our number of turns in the secondary coil is what we do not know. Then the number of turns in the primary is 5,500, right? So from here, before I even do anything, I can cancel the 0 over here. Okay, so from here I have 12 over 24, okay, is equal to NS over 5,500. So from here I can cross multiply. Okay, I can cross multiply. This will multiply this, this will multiply this. So from here I have 24 NS is equal to here 12 multiplied by 5,500. Okay, to find NS, I divide both sides by 24 by 24. This will cancel this. So my NS is equal to 12 will go into itself 1, will go into 24 2 times. Okay, so this becomes 5,500 divided by 2, and this will give me 2,750 turns. Okay, so this is the number of turns on the secondary transformer. So we have 2750 turns. Okay, now if you look at it, the number of turns in the primary transformer is 5500, and half of it is what we have on the secondary transformer. So it means if this is the my transformer, okay, it means let me use, this is 5, so let me use the primary, let me use 5, 1 2 3 4 5, right? It's more than that, but I'll just use the first digit. So this is like, let me say 2.5, right? So this is 1 2 something like this, right? 3, let me make it like that, right? So if you look at this, this is obviously a step down transformer, okay, because the input voltage, even if you are not using the number of turns, the input voltage is 240 over here, and then it is giving you a 120 voltage for your electric kettle to be able to use, right? It doesn't blow, right? So it is stepping down the EMF for you. So this is obviously a step down transformer. Are you okay? All right, let's look at the next question. We have a transformer which has a 300 turns of wire in the primary coil and 30 turns in the secondary coil. If the input voltage is 100 volts, we have to find the output voltage, right? Now, already from reading the question is saying a transformer has 300 turns of wire in the primary coil. So the primary coil has 300 turns, and the secondary coil has 30 turns. This is also a step down transformer, right? Because of the number of coils that we have in both primary and secondary sources. So if the input voltage is 100, find the output voltage. So from here, we know that since it is a step down transformer, the output voltage should be smaller than the input voltage. So if I get an answer which is more than 100, I should automatically know that my answer is wrong, because it is a step down transformer, and so therefore my secondary voltage or my output voltage should be less than the input voltage. All right, so let's write down our solution. Okay, so they say the number of turns in the primary coil is 300, and then it has 30 turns in the secondary, so NS is 30. The input voltage E primary is 100 volt, and then we have to find the output or the secondary voltage. That is what we do not know. Okay, so just like we did before, we have our secondary EMF over primary EMF is equal to the number of turns in the secondary over the number of turns in the primary over here, right? So from here, let me make ES the subject. So I'll first of all cross multiply. So ES multiplied by NP is equal to EP multiplied by NS. So I have EP here multiplied by NS, right? So we want to find ES, so I divide both sides by NP. So this will cancel this. So my ES is equal to my EP is 100, which is my primary voltage, multiplied by my secondary turns, which is 30, divided by primary 10 NP, which is 300, right? So from here we can compute to find our output voltage. So the 0 here will cancel the 0 here. The second one will cancel this over here. So I have 10 multiplied by 3 at the top. That will give me 30. Then I have 3 at the bottom here. So this is equal to what? 10. 30 divided by 3 is 10. So 10 volts is my answer. And like I said, obviously the output voltage is smaller than the input voltage. So it's 10 to 100. So it is a step down transformer, like I said, and this proves that my answer is indeed correct. All right, let's have a look at one final example. So they are saying if the efficiency of a transformer is 80% and the current in the secondary coil is 10 amperes, we are to calculate the current in the 240 voltage supply provided the output voltage is 24 volts. Are you okay? So this is also a very simple problem. So let's write down our solution and look at it. They said that the efficiency of the transformer, the efficiency, okay, the efficiency is 80%. Okay, and then the current in the secondary core, so is, is 10 amperes. We have to calculate the current in the, okay, so in the, so we have to calculate the primary current, which we don't know, in the 240 voltage supply. So supply means what? EP is a 240 volts. If the output, which is ES, is what? 24 volts. Are we okay? All right. So if you look at this, we are looking at a supply voltage, a primary voltage of 240, supply voltage of 24. So obviously this is a step down transformer. All right. So when we talk about the efficiency of a machine, okay, is equal to in power input, okay. So power output over power input multiplied by 100, right? That is what is going to give you the efficiency, right, in percentage. Okay, so we can divide this, since this is multiplying this, so to get rid of the 100 over here, so we can leave that like that. So let's leave it like this for now. So the efficiency, when you have this in percentage like we have over here, then you take off the 100 over here. So if you have the efficiency already given to you in percentage, it's just equal to what? Power output over power input, right? Because the percentage has already been brought over to this side. Okay, so which is what we are going to do now. What is power output? Power output is voltage times current. So obviously it's equal to ESIS. This is the power output. Okay, then the power input is EPIP. That is the power input. So the efficiency, we are going to use this version of the formula. The efficiency given to us is 80%, so it's 80 over 100, which is equal to our power output is ES multiplied by IS over EP multiplied by IP. So I have my 80 over 100, which is the 80%, is equal to my ES is 24 multiplied by my IS, which is 10, all over my EP, which is 240 multiplied by IP, which I do not know. So from here we can go on and do some few cancellations and then get our answer. Obviously this will cancel this, so we are done with this side. The top over here, if you multiply 24 by this, so let me make it like this, this is 8 over 10 is equal to, this multiplied by this is 240 over 240 multiplied by IP. So this will go into itself 1, go here 1, right? So we have this is equal to 8 over 10 is equal to 1 over what? IP, because this has cancelled each other out. So 8 will, it will cross multiply over here. Okay, so it becomes 8 IP is equal to 10. Okay, 10 multiplied by the 1 at the top. So we divide both sides by 8 by 8. So therefore our IP will be equal to 10 divided by 8 will give us 1.25 amperes as my answer, right? So this is my answer for this particular problem. And now if you look at it, because we are saying that the primary voltage is more than the secondary voltage, we are saying this is a step down transformer. Now because it's the step down transformer, and then the relationship between the current and then the EMF is inversely proportional, you can see that even though the primary voltage is more, the current in the primary coil is also lower than the secondary one. Are you okay? So which makes sense, but the number of turns will be more. The number of turns is directly proportional to the EMF, but inversely proportional to the current. So that makes sense. So thank you so much for watching. This is just some few questions on transformers. We'll be looking at more questions, and then we'll move on to the past questions related to transformers. Okay, in this video we want to look at more examples on transformers. Now, in our previous video we did look into detail about what transformers are, the type of transformers that we have, and all the necessary formulas that we need, to do calculations on transformers. Now, in this video we want to look at some two questions that contains a lot and get to bring out our thinking ability. After that, we'll look at the past questions in the third part, and then everything together will be one full complete tutorial. So we have an example here. Let's look at it. The voltage from an alternator is 500 volts and it is fed into a step up transformer. Are you okay? Now this tends to be fed into an overhead cables with voltage of 20,000 voltage. We are to calculate the required turn ratio. B, we are to calculate the number of turns of the secondary coil if the primary coil has 26 turns, and then C, if the power of the generator is 100,000, okay, or 100 kilowatts, we have to calculate the current fed into the cables, right? Now this is fairly simple. Let's look at the solution to this problem. So we write down our solution. Okay, so let's write down the parameters that we have. So they say the voltage from an alternator is 500 volts and it is fed into a step-up transformer. It means our primary voltage, which is EP, is equal to what? 500 volts, right? Now, if this tends to be fed into an overhead cable of, okay, so which is then fed into a cable after the transformer has done its thing or has done stepping up the voltage, it is fed into an overhead cables and the voltage is 20,000. So it means our secondary voltage is 20,000. 1, 2, 3 volts. Okay, so A, we are to calculate the required turn ratio. Okay, now in our previous video when we look at transformers, we said that the ratio of the secondary voltage to the primary voltage is equal to the ratio of the primary current is to the secondary current, which is also equal to the number of turns in the secondary coil and then the number of turns in the primary coil. This is the expression that we have. So we can use any of this, either this or this, to calculate the required turn ratio, right? In this case, since we only have the voltage given to us and then we don't have this is the turn ratio, the ns over np, that's the turn ratio. Since we don't have this, or this is what we are supposed to find, and then we've been given this, we can equate this and this, and then we can find our turn ratio. So our turn ratio, ns over np, will be equal to es over ep. So I'm just lifting it from here. So this guy over here is equal to this guy over here, right? That is what we have. So ns over np is what we call the turn ratio, and that is what we are finding. So in this case, ns over np is equal to our es, which is the secondary voltage over here, is 20,000 divided by our primary voltage, which is 500. So if we look at that, these two zeros will cancel this, and then 5 will go into 24 times. So with the 0 left over here, so it becomes 40. So we have 40 is to 1 over here. So therefore, okay, our turn ratio, or the number of turns in the primary, in the secondary, to the number of turns in the primary, is equal to 40 is to 1. Okay, so this becomes our answer. This becomes our turn ratio, right? 40 is to 1. Okay, so let's look at the B. So the B is saying we have to calculate the number of turns of the secondary coil if the primary coil has 26 turns. Okay, so let me find a space here to squeeze it in. So before that, let me get just some small space. So let me erase this. We've already said that this is the 10 ratio. Okay, 40 is to 1. Are you okay? So if that is the case, let's look at B. B is saying that we have to calculate the number of turns in the secondary coil, which we represent by NS. If the primary, so this one is unknown, if the primary turns is 26 turns. Okay, if the primary turns is 26 turns, this is what we have over here. Now we've already established that the ratio of NS to NP is what? 40 is to 1, okay, from the A aspect. So if that is the case, then we can say this implies that our NS we still don't know, so we maintain our NS, but our NP has been given to us as 26, so this will be equal to 40 divided by 1. So from here we cross multiply, this will multiply this will multiply this. So I have NS multiplied by 1 is equal to 26 multiplied by 40. Are we okay? So from there, 26, sorry, this is supposed to be 25 tenths. Okay, it's supposed to be 25 tenths. So we are dealing with 25 tenths, 25 over here. So this is also 25. So let me use another color for that. Okay, but regardless whether it's 25 or 26, the answer you will get is just simply multiplication. So this side is going to be 25, okay, multiplied by 40, and then if we do that, it's going to give us 1,000 turns. Okay, so it means that the number of turns in the secondary side is 1,000 turns. Are you okay? So this is the answer for the B part. All right, so now that we've calculated the 10 ratio, and then we've also looked at the number of turns in the primary, which is 25, and that of the secondary, which is 1,000, which tells us since the number of turns in the primary is lesser than the number of turns in the secondary, it tells us that it is indeed a step up transformer. If you've watched the first part of the tutorial, you will understand what we mean by this. All right, so from here, let's look at the C part, which says that if the power of the generator is 100 kilowatt, we have to calculate the current fed into the cables. Right now, remember the current fed into the cables, okay, the overhead cables, the current fed into that cable becomes the current output, right, or I secondary or IS. That is that. So let me get some space, and then we quickly look at the solution to that particular side. Okay, so let's look at that. So we've been asked that if the power of the generator, so the power of the generator, okay, is 100 kilowatts. Okay, we have to calculate the current fed into the cables. Right now, if you look at this, the current fed into the cables is the IS, or the secondary current. Okay, the current from the power into the transformer is the IS. So we have the primary current, are you okay, and then we have the secondary current, okay, which the question is demanding that we find. So first of all, we need to determine the primary current from the power given to us. Now remember, we've established the fact that the secondary voltage is 20,000 from the question, and then the primary voltage, okay, or EMF is given to us from the alternator, which is 500 volts. We already have this. So if that is the case, power, okay, so I'll make it P subscript P. That means the power fed into the primary core, okay, is equal to the voltage, which is the EP, multiplied by the current IP. Are we okay? So therefore, from here, to find the initial current, or the current fed into the primary core, it means that IP is equal to the power, okay, divided by the EMF, right? It means we divide both sides by EP here, EP here. So this will cancel this. Our IP becomes PP over EP, right? Now these are just initials, right? So our answer over here is that our power, which is 10, which is 100,000. K is times 10 to the power 3, so 3 more zeros over the initial potential difference, EP, is 500. So I bring my 500 over here. So therefore it implies that my primary current is equal to 100,000 divided by 500, and this will give me 200 amperes as my answer. Now that I have my current, there are so many ways I can go about this to find the answer. I can either use E secondary, EMF in the secondary coil over EMF in the primary coil is equal to current in the primary coil over current in the secondary coil to find that, or I can also use the current in primary over the current in secondary is equal to the number of turns NS over NP. I can also use this. Now mind you, NS over NP, we've already found a ratio for it, that is 40:1. So we can use that as well. So any of this will actually give you the final answer, so long as you quote the formula really well. So I will be going with okay, I'll be going with this, right? But we can also use this. So in fact, let's use both and see if we'll get the answer, right? So using this first, our IP, which is 200, so I have here 200 over IS, which I'm supposed to find, is equal to NS over NP, right? The NS over NP, the ratio is 40 is to what? 1. We've already established that. So therefore, this means that the 200 will multiply the 1 over here. So we have 200 is equal to 40 IS. So to find IS, we divide both sides by 40 by 40. So our IS will be equal to, this will cancel this, this will also cancel this. So 20 divided by 4, that will give us 5. So we have 5 amperes as our answer. Or we can also use this side. So let me use a different color to show that one. So our ES is 20,000, okay, which is this guy, over our E primary, which is 500. And that is equal to our IP, which we found is 200 over our IS, okay? So if we cross multiply, we realize that we will have 20,000 IS is equal to 500 multiplied by 200, right? So we can divide both sides by 20,000. This will cancel this, right? So here we just cancel a bunch of zeros. This 1 0 will cancel this, the second one will cancel this one, the third one will cancel this one will cancel this guy. Are you okay? And even the 2 will cancel the 2 over here. So we are left with 5. So therefore our answer over here, IS, is 5 amperes, right? So regardless of whether we use this expression or this expression, we are still getting 5 amperes as our answer. Very good. All right, so let's have a look at another problem, and then we end the second part of this tutorial. So we have a transformer has a primary coil of 500 turns and a secondary coil of 25 turns. This one is pretty straightforward. So we've been asked A, what sort of transformer is it? B, we have to calculate the turn ratio. Very easy. C, if the primary coil is connected to a 240 volt mains, we have to find the voltage in the secondary coil. Also very easy. We also to calculate the efficiency of the transformer if the primary current is 0.6 amperes and the secondary current is 8 amperes. Very easy, straightforward. Let's dive in. So we write down our solution. So the transformer has a primary coil of 500 turns. So our number of turns in the primary is 500 turns Okay, and then the secondary coil has 25 turns, so our NS is 25 turns. Okay, now they are asking us what sort of transformer is this? Now, if the primary coil has more turns than the secondary, this is a step down transformer because it is moving from 500 to 25. So it's a step down transformer, right? But if it is moving from, let's say, a lower number in the primary to a higher number in the secondary, it is a step up. So this is a step down transformer. That is the A. Now the B is saying we should calculate the turn ratio, right? Now the turn ratio is either NP over NS or NS over NP, regardless of how you want to do it. So it's either this over this over NP. So let me do it over here. So B is either NS over NP, okay, depending on how you want to do it. So I'll use this. So NS is 500. NS is 25. So let me clear that. So let me clear this. So our NS is 25. Our NP is 500. Okay, so this will cancel itself one. It will go into 52 times. So with this 0 come down by is 20. So the ratio is 1 over 20, right? So therefore, it means that our NS is to NP is equal to 1:20. So the ratio is what? 1:20. It can also be 20:1 if you bring the NP first is to NS, then it will become 20:1, right? Regardless of how you position it, it is still going to be correct. Now let's look at the C part. The C is saying if the primary coil is connected to, so the voltage passing through the primary coil is 240 volts. Okay, we have to find the voltage in the secondary. We have to find the ES. That is what we do not know, right? Already we have the ratio of NS to NP, so we can just use that in conjunction with this, and then we will get our answer. So for this ES, okay, the secondary voltage over the primary voltage is equal to the number of turns in the secondary over the number of turns in the primary. This is the ratio we'll be using. Are you okay? So from here, to make the secondary voltage the subject, ES will be equal to this will multiply this, this will multiply this. So we'll have EP multiplied by NS, okay, this and this. So we'll divide it by NP. So divided by NP. So that is it. So this will be equal to our EP is 240 volts multiplied by the number of turns in the secondary, which in terms of ratio, the NS is 1. So we'll use 1 over here over the number of turn in the primary is NP over here, which is the 20 at the bottom here. So we have 20 over here. So this is basically 240 divided by 20, and then that will give us, if you compute that, that will give us 12. So our answer is 12 volts, right? It is 12 volts. Now, because it is a step down transformer, we can see that the voltage that is applied to the transformer is 240, but it has reduced it to 12 volts. Are you okay? And this also proves that our answer for A, which is a step down transformer, is correct, because a step down transformer steps down the voltage or reduces the voltage output compared to the input. All right, so now that we have this, let's go ahead and look at the D option of this particular question. Now the D is saying that we should calculate the efficiency of the transformer if the primary current is 0.6 and the secondary current is 8 amperes, right? So let's have a look at that. Okay, so D, we have to calculate the efficiency, right, of the transformer. So we are told that the primary IP current is 0.6 amperes, and then the secondary current IS is what, 8 amperes. Now, the efficiency of a transformer, let me make it like this, is equal to power output, okay, over power input multiplied by 100, that is it. Now, for power output or input, power output, which is let me make it power output, P subscript O, it means the power in the secondary core, okay. So that would be the voltage in the secondary core multiplied by the current in the secondary core. Now, the power input, which I'll make Pi, is equal to the power in the primary core. So that would be potential difference, or EMF in the voltage in the primary core multiplied by the current in the primary core. So this is effectively equal to ES IS over EP IP multiplied by 100, which is equal to the ES is what we found is 12 multiplied by the IS as 8 over here. Then we divide that by, remember we are multiplying all by 100. Then we divide that by our E primary is 240 multiplied by our current in the primary is 0.6 over here, right? So 12 multiplied by 8 will give us 96, and then 240 multiplied by 0.6 will give us 144. Okay, then all of this multiplied by 100, and this will give us a percentage of 66.67%, right? So it means that the efficiency of the transformer is this, right? But if you were asked to convert it to the nearest whole number, then this becomes 67% efficiency, 67% efficiency for the machine. So thank you so much for watching. This is how we solve some further questions on transformers. So in the next video, we'll be looking at some past questions, objectives on these transformers, and then we will look at some other past questions which are subjective as well, to further enhance our understanding of transformers, and then we put all the videos together to make one full tutorial. In this video, we want to look at the third part of our transformers lecture or video series. So we are looking at some objective questions that came on transformers for WASSCE or WAEC candidates. So let's look at the first example we have over here. We have a transformer delivers a current of 10 amperes at 30 volts. If the primary coil of the transformer draws a current of 4 amperes from a 120 volt supply, we have to calculate the efficiency of the transformer. Now this is very easy and very straightforward. So let's look at the solution. Right, so if you're watching this video, I believe you've already watched either the first part or the second part of our transformer videos, and you've seen how we solve problems like this, and you've seen the formula and you know the formula, right? So here we have a transformer that delivers a current of 10 amperes at 30 voltage, right? So we were told that if the primary coil of the transformer draws a current, so it means the current in the primary coil, which is IP, is 4 amperes from a 120 voltage supply. So it means the voltage supply, which is EP, is a 120 volt, right? So it means the current given to us over here is the current in the secondary coil, which is 10 amperes, and then the voltage is the voltage in the secondary coil as well, which is 30 volt. So we have to calculate the efficiency of the transformer. Now to calculate the efficiency of a transformer, the efficiency is equal to power output over power input multiplied by 100, right? Now power output is equal to the product of the voltage in the secondary coil multiplied by the current in the secondary coil. So basically it is ES multiplied by IS, right? The voltage in the secondary coil multiplied by the current in the secondary coil, that's the power output, and then the power input is equal to the voltage in the primary multiplied by the current in the primary. So this is basically like ES IS over EP IP multiplied by 100, right? So this is equal to our ES is 30, so we have 30 multiplied by our IS is 10, then divided by our EP is 120 multiplied by our IP, which is 4, then all multiplied by 100. Are we okay? All right, so if you look at this, we have 30 multiplied by 10. Our efficiency is equal to 30 multiplied by 10 is 300, divided by 120 multiplied by 4 is 480, then multiplied by 100. So the efficiency is equal to 300 divided by 480. That will give us 0.625, then multiplied by 100, and then this will therefore give me 62.5% as the efficiency of this particular transformer. Okay, now here is a question based on the voltage, right? The primary voltage and then the secondary voltage. Which kind of transformer are we dealing with? Okay, now if you say a step down transformer, you are correct, because the primary voltage is higher, the secondary voltage is lower. So it means you provided the transformer with a 120 voltage supply and you want it to reduce it to a 30 voltage supply. So this, okay, from a bigger to lower value is what we call the step down transformer. Okay, step down transformer, right? In as much as the voltage is reducing from 120 to 30, you can realize that the current inside is rather increasing, right? That is the relationship, right, between the voltage and then the current. They are inversely proportional when it comes to transformers. All right, so let's have a look at another question. So we have here the primary coil of a transformer has 3000 turns. If the transformer is required to give 20 voltage from a 240 voltage main supply, we have to calculate the number of turns of the secondary coil. So this is the SSC 1999 question number 39. All right, so let's write down the solution to this problem. So we're told that the primary coil of a transformer has so the NP, the number of turns in primary, is 3000 turns. Okay, now if the transformer is required to give this 20 voltage from 240 main supply, it means our supplied voltage, which is EP, is 240 volts, and then our secondary voltage, which we are expecting, is 20 volts. Are we okay? So we have to calculate the number of turns in the secondary, so we have to calculate NS. That is what we do not know. Are we okay? So this is fairly easy, very easy. So for this particular question, the current or the voltage, the voltage in the secondary, the ratio of the voltage in the secondary to that of the primary is equal to the number of turns in the secondary over the number of turns in the primary. This is the ratio that we have. Are we okay? So if we make NS the subject over here, we are going to, first of all, we'll cross multiply. Are we okay? So this will give me my NS EP is equal to ES NP, right? So I divide both sides by EP. So this will cancel this. So the number of turns in the secondary is equal to my ES, right, which is 20 volts, multiplied by the number of turns in the primary, which is 3000, over the EMF in the primary, which is 240. Okay, so if I compute all of this into my calculator, okay, I'm going to get 250 turns, okay, as the number of turns in the secondary coil. Are we okay? All right, so this is the solution to this particular problem. All right, so let's have a look at another example. So over here we have the current in the secondary of a transformer and the potential difference across it are 0.4 amperes and 240 volts respectively. We are to calculate the current in the primary if the potential difference across it is 20 volts. Remember that the efficiency of the transformer is 80%. Okay, actually this is the SSE 2001 question number 35. Question number 35. All right, objective question. Okay, then again, like I said, let's look at the solution to this problem. So let's first of all write down our parameters. They say the current in the secondary of a transformer and the potential difference across it is this and this. So it means the current in the secondary is 0.4 amperes, and then the voltage in the secondary ES is also equal to 240 volts. Are you okay? We have to calculate the current in the primary. So IP is unknown if the potential difference, which is EP, is equal to 20 volts. Remember, we're given that the efficiency is equal to 80%, right? Now if I look at this, the voltage in the primary is 20, the voltage in the secondary is 240. It means that the transformer was supplied a lower voltage to produce a higher voltage, which is what we call a step-up transformer, right? All right, so let's look at the solution to this particular problem. Now if we are given efficiency, okay, is equal to power output over power input multiplied by 100, right? So if we want to get rid of the 100 over here, we divide both sides by 100, right, to get rid of the 100, or we can leave it like this. So basically it means that our efficiency is equal to the power output is ES IS over power input is EP IP multiplied by 100. Are we okay? Now this is the formula that we're going to use to solve our problem, right? So if I want this to use this as 80%, it means that this is already in percentage, so I can get rid of this over here, right? So I'll divide both sides by 100, both sides by 100. So this by hand divide, so this will cancel this over here, and then we'll have this over here. So basically it means that my efficiency over 100 is equal to ES IS over EP IP, right? So my efficiency is 80, so it's 80 over 100. Are we okay? Either that, right, or if you are confused over here, basically what it means that once you quote this formula, okay, in place of the efficiency over here, if you use 80, then you maintain the 100 over here. But if you want to use 80%, as in 80 divided by 100, then the 100 has to go away from here. Are we okay? That's basically why I am doing all these things, right? So 80 over 100, which is the 80% I'm using over here, so the 100 will no longer be here. So this is equal to the ES, which is 240, multiplied by the IS, which is 0.4, over the EP, which is 20, multiplied by IP. All right, so here I cross multiply. Okay, so I have 240 multiplied by 0.4 multiplied by 100 is equal to 20 multiplied by IP multiplied by 80. So to find my IP, so my IP will be equal to all of this divided by 20 multiplied by 80. 20 multiplied by 80, right? So this will get rid of this, this will get rid of this. So my IP is equal to 240 multiplied by 0.4 multiplied by 100, or divided by 20 multiplied by 80. Right, so my primary current, if I do my cancellation and everything over here, I'm going to get 6 amperes as my answer for the current over here. So the current over here is 6 amperes. So if you look at it, you realize that even though the primary voltage is low, okay, and then the primary current is high, the resulting current that is produced in the secondary coil is lower, but then the voltage is higher. That's the typical job of a step-up transformer, because the relationship between the voltage supplied and the current is inversely proportional. So EP is equal to 1 over IP. Okay, so this is the relationship between them. So thank you so much for watching. This is some WAEC past questions that came on transformers. There are more, but I think these 3 examples is enough for you to wrap your head around how to solve any problem that comes with transformers. So I'll combine the first lesson, the second lesson, and this particular one together in one to make one full video tutorial on transformers. If you need further assistance, you can drop a comment in the comment section below, or you reach out to us at mysciencetutorial@gmail.com. But don't forget to subscribe to the channel so you don't miss any video from us. Like the video, share with colleagues and friends,